Welcome everyone to this series of videos about the SCION secure internet architecture. Since summer 2009, we have been working on this project. So why would we spend 8 years to study a new internet architecture if the current internet is working just fine? In the next 2 videos, we will explore what aspects of the internet we would like to change and why we need a new internet. So first, imagine a building or structure that would represent the internet. You may think of the pyramids, an ancient structure that appears stable and reliable and seems unchangeable. Perhaps the internet is not quite ancient, but since its creation in the 70s and 80s, it has seen relatively few technological changes in its fundamental operation. So in terms of technology, it is thus in fact quite ancient. However, I'd like to argue that a structure that better represents the internet than the pyramids is this Greek column. Also ancient, but in contrast to the pyramids, much more unstable and brittle. In fact, the more you know about the internet, the more you are surprised that it works as well as it does. We're going to illustrate the shortcomings of the current internet based on 4 aspects: availability, control, transparency, and secure end-to-end communication. Let's start by looking at availability. The internet has a surprisingly poor level of availability. It appears to work fine most of the time, and since we cannot accurately see the true reason for a failed connection, we usually attribute times when the internet is not working to a problem of the server or perhaps our own computer. But in fact, the internet has a lot of outages, and even for a well-connected entity, you only get about 3 nines of availability, which is to say that during about 90 seconds per day, your internet is unavailable and you cannot reach other entities. Compare this to an ancient plug-into-the-wall telephone. It has 5 nines of availability, so only about 1 second a day of unavailability. The reason the internet has such low availability is that there are numerous short-lived outages due to the Border Gateway Protocol, which is also called BGP. And this BGP protocol has route changes and route convergence delays. And relatively frequently during such route changes, there's a short-term loop that exists. And so for a short amount of time, perhaps 2 to 3 seconds, there's actually a brief outage. There are also outages due to misconfigurations. And we've seen that misconfigurations at one end of the world can affect the internet connectivity on the other end of the world. There are also outages due to attacks. So for instance, prefix hijacking or distributed denial of service attacks can result in internet outages and lower your availability. So all in all, the availability of today's internet is really quite poor. Secondly, let's talk a bit about control. And here, the question is who controls internet paths? And the current internet actually offers quite a limited control of networking paths. In fact, paths can be hijacked and redirected. So in this example, which was reported by the company called Renesys, and they're now called DIN, they've looked at different instances where network paths have been hijacked and routed around the different part of the internet. So in this example here, we see a path from Guadalajara in Mexico to Washington, D.C. And in the normal case, the packets would follow this green path. But unfortunately, based on a internet route hijack, the path was redirected through London, then Moscow, then Minsk, and Frankfurt, back to Washington, D.C. And what's interesting is that the actual entities who are communicating may not realize that this is happening. In fact, they can just see that the latency of network packets increased because they now traverse across the Atlantic Ocean twice. But other than that, the internet connection seems to be fine. Here's a second instance that Renesys has documented. And in this case, the traceroute path is from Denver to Denver. And in normal case, funny enough, it goes via Dallas and Kansas City. However, in this case, the traffic got redirected through London and Reykjavik before it reached its destination. In a third instance, traffic from New York to LA was redirected through London, Moscow, and Minsk. And in this fourth example, traffic from Chicago to Tehran got rerouted again through Moscow, Minsk, then back to New York, and then finally to Tehran. So each packet would cross the Atlantic Ocean 3 times before reaching the destination. So the BGP protocol, this border gateway protocol, actually offers quite limited opportunity to control paths. And I'm briefly going to demonstrate this based on this example here. We see a number of nodes in a network, and in particular a green node and an orange node. We're going to look at BGP announcements for the destination of this green node. And we want to demonstrate that there is no inbound traffic control that BGP offers. So in this example here, the green node issues routing beacons, BGP update messages that traverse the network. And these update messages reach other entities, and they now can select how to reach the green node. So in particular, this orange node would receive this blue path and the red path. And now this orange node can select whether he wants to use the blue path or this red path in order to deliver packets to this green node. And there's very little the green node can do to influence this path choice. And thus, we can see that BGP today offers very limited amount of ingress traffic control. If we ask the question, who should actually control paths in today's internet? So clearly, ISPs should have some amount of path control to enact their routing policies. And ISPs represent internet service providers. So the question is, how much path control should end domains and endpoints actually have? And we see at the bottom, there's a range of the amount of control that can be achieved. So on one side, we have no endpoint control at all. On the other end, we have complete endpoint control. And both of these extreme cases are undesirable. Clearly, the endpoint should have some amount of control, but complete endpoint control is represented by source routing, and that would also offer opportunities for performing network attacks if endpoints would have complete path control. Also, source routing itself is not very scalable. So we need to be somewhere in between no endpoint control and complete endpoint control. The question is, where is the right point? And we're going to answer this question when we talk about the SCION architecture. So we're going to argue that the limited amount of control offers meaningful path selection for end hosts, not complete endpoint control, but also at least some amount of control that is meaningful. So you may wonder, well, path control is really not that important. Why would I care? Because all I want is that my web page would load and my movie plays. So why do I really care about path control? Well, it turns out that path control is quite important. Path control enables traffic load balancing for senders and receivers. And also, with the absence of path control, you can't really have any meaningful multipath communication, because in practice, you would like to use several different networking paths between a source and a destination. Then this also allows optimization of paths while you're communicating and sending traffic across the best path at a given instant in time. A lack of path control can also lead to poor availability. So for instance, a network outage cannot be circumvented. Or also a network link can suddenly break, and then you don't have an easy way to circumvent this network link. Also, traffic redirection attacks become possible, as we've seen, with the absence of path control. So as we see, path control has a lot of benefits that we would like to take advantage of in a future internet. Next, we're going to look at transparency. And there are different aspects to transparency. First, let's briefly talk about path transparency. So today, a sender cannot obtain any guarantees that a packet will travel along a certain path. And the reason is that routers with forwarding tables can update these forwarding tables at an arbitrary point in time. Now, the problem is that even if the sender would know the entire forwarding state of all the routers on the path, one cannot know that a router would not update its table after a packet has been sent. So even in that extreme case, where all the forwarding tables are known, the sender still cannot achieve assurance about the networking path that the packet will take once it's sent. The second aspect of transparency is trust transparency. So it turns out today we cannot enumerate the trust routes that we rely upon. In fact, there are many trust routes that we don't know about, yet for secure connection establishment, we actually rely upon them. And what we would like is an internet architecture where one can exactly know which trust routes they need to rely upon in order to set up secure connections. The fourth problem we're going to look at is the problem of secure end-to-end communication. And in this context, it turns out that in today's internet, there are opportunities to run attacks on secure point-to-point communication. So consider this example. We have Alice and Bob that intend to communicate, and typically they make use of what's called digital certificates in order to set up a secure connection end-to-end. Now, the attack that can happen is that Mallory, an adversary, can present a bogus certificate either to Bob and or Alice, and in consequence set up a separate secure connection with each of them. And this is what's called a man-in-the-middle attack. So Mallory would set up a key with Alice and a different key with Bob, but Bob and Alice think they're directly communicating with each other. Now Mallory can decrypt all communications sent from Alice to Bob and vice versa. And it can also inject malicious information. Basically, a bogus SSL or TLS certificate is being required to perform such man-in-the-middle attacks. And in the past decade, we've seen several instances where such attacks have happened in practice. So the observation is that trust is actually quite non-scalable. So as the internet has grown to encompass a large part of the global population, trust relationships have become heterogeneous. So there's no single entity that's trusted by everyone, and also the mutual trust relationships in the world can be quite complicated. And this itself complicates the construction of entity authentication infrastructures. In fact, the current internet authentication infrastructures have quite weak security properties. They suffer from single points of failure, as well as the problem of security of the weakest link. And clearly, we'd like to have stronger ways to set up secure communication. So in summary, which problems should we address? First of all, we'd like to achieve high levels of availability to enable end-to-end connectivity despite network disruptions and even despite malicious activity in the network. We'd also like to achieve path control, such that not only ISPs, internet service providers, but also senders and receivers can jointly control end-to-end paths. We'd also like to achieve transparency, in particular, path transparency, so that the sender is aware of the path that a packet will take, as well as trust transparency, such that all the roots of trust can be known that need to be relied upon. We'd also like to have resilience to compromise trust routes, so to limit the global scope of certification authorities that issue certificates. So we're getting away from these systems that are only as strong as the weakest link and have no single point of failure. Would you like to learn more? In the next video, we're going to continue to explore more reasons why we need a new internet. For more information, please visit our website. Chapter 1 of our SCION book discusses the material we've seen in this video in more detail. You can purchase the book from Springer Verlag, or you can download the PDF from our website. Thank you for watching.